Hi. I am Zira, and also from Microsoft, USA. I am taking over from David for the next section, where we discuss crude oil as a major source of fossil energy, as well as chemicals in the form of petrochemicals. You will be provided with its definition, its source, composition, and properties, processing methods, and the range of products you can derive from crude oil. By the end of this section, you are expected to be able to define crude oil as a complex mixture of hydrocarbons. Secondly, to describe how the process of fractional distillation can be employed to separate the hydrocarbons in the crude oil into its constituent fractions of refinery gases, gasoline, kerosene, diesel, petrol, fuel oil, bitumen, and other constituents. To describe the physical properties and uses of the main fractions, and to recall that the fractional distillation of crude oil produces more long-chain and fewer short-chain hydrocarbons than required. The accompanying diagram depicts oil extraction by means of a well, through fractionation, and, if required, further processing and mixing to produce the final products. In this slide, you are going to be introduced to the composition of oil. Crude oil, or liquid petroleum, is found in various porous rock formations in the Earth's crust. It occurs underground, at various pressures depending on depth, and it can contain considerable amounts of natural gas as well, which is kept in solution by the pressure. Crude oil is a mixture of comparatively volatile liquid hydrocarbon compounds, which are compounds composed mainly of hydrogen and carbon, though they also contain some nitrogen, oxygen, and sulfur. These elements form a large quantity of complex molecular structures, some of which cannot be readily identified. Regardless of variations, almost all crude oil ranges from 82 to 87% carbon by weight, and 12 to 15% hydrogen by weight. Crude oils are mainly characterized by the type of hydrocarbon compound that is most prevalent in them. For example, paraffins, naphthenes, and aromatics. Paraffins are the most common hydrocarbons in crude oil. Certain liquid paraffins are the major constituent of gasoline, petrol, and are therefore highly valued. Naphthenes are an important part of oil liquid refinery products, but they also form some of the heavy asphalt-like residues of refinery processes. Also, aromatics generally constitute only a small percentage of most crudes, the most common of which is benzene, a popular building block in the petrochemical industry. The composition of crude oil from various sources will not be uniform, but will depend on the crude oil source, the nature of the composition of elements within the geological where it exists, the original flora and fauna that contributed to its formation, as well as the specific conditions of temperature and pressure, geological depth, the geological surrounding composition, and the source. Because crude oil is a mixture of such widely varying constituents and proportions, its physical properties also vary widely. In appearance, for instance, it ranges from colorless to black. Possibly the most important property is specific gravity, that is the ratio of oil to pure water under standard conditions. In the measurement of specific gravity, it is customary to assign pure water with a specific gravity of 1. Substances lighter than water, like crude oil, will have a specific gravity of less than 1. However, the petroleum industry uses the American Petroleum Institute's gravity scale API, in which pure water has arbitrarily been assigned a API gravity of 10 degrees. Liquids, lighter than water, such as oil, have an API gravity numerically greater than 10. On this basis of the API gravity, crude oils can be classified as heavy, medium, and light as follows: heavy ranging from 10 to 20 degrees API gravity, medium, 20 to 25 degrees API gravity, and light above 25 degrees API gravity. Crude oil is also characterized as sweet or sour depending on the level of sulfur, which occurs either as elemental sulfur, or as compounds such as hydrogen sulfide. Sweet crudes have sulfur levels of 0.5%, or less, by weight, and sour crudes have sulfur content of 1% or more by weight. Generally, the heavier the crude oil, the higher its sulfur content. Excess sulfur is removed from crude oil during refining, because sulfur is oxidized during combustion of oil and released into the atmosphere as a major pollutant. This is why, in a petrol station by a pump, you will have diesel classified specifically as 50 ppm and 500 ppm sulfur. It is important to note that diesel, that is produced from the coal to liquid or gas to liquid processes, via the Fischer-Tropsch reaction process, can be produced as zero sulfur. As before, the accompanying diagram depicts oil extraction by means of a well, through fractionation, and, if required, further processing and mixing to produce the final products. In this slide you will focus on extraction, desalting and dewatering, and storage. In addition to oil, water often flows into an oil well along with liquid crude and gas. All these liquids are collected by surface equipment for separation. Desalting and dewatering. In this stage, crude oil is recovered from the reservoir mixed with a variety of substances, gases, water, and dirt, minerals. Desalting is a water washing operation performed at the production field and at the refinery site for additional crude oil cleanup. If the petroleum from the separators contains water and dirt, water washing can remove much of the water-soluble minerals and entrain solids. If these crude oil contaminants are not removed, they can cause operating problems during refinery processing, such as equipment plugging and corrosion as well as catalyst deactivation. Clean crude is sent for storage at close to atmospheric conditions, usually above ground in cylindrical steel tanks that may be as large as 30 meters in diameter and 10 meters in height. As before, the accompanying diagram depicts oil extraction by means of a well, through fractionation, and, if required, further processing and mixing to produce the final products. In this slide you will focus on the transport of oil to, and the storage at the refinery, as well as the pipe still furnace heating. Often, the crude oil needs to be transported from widely distributed production sites, to treatment sites and refineries, usually via pipeline. Crude from more isolated wells is collected in tank trucks and taken to pipeline terminals. There, some special transport is provided, such as railroad cars. Overseas, transport is conducted in specially designed tailored ships, with capacities varying from 100,000 barrels to more than 3 million barrels, to oil refineries. After transport, crude is stored, as before, at close to atmospheric conditions, usually above ground in cylindrical steel tanks that may be as large as 30 meters in diameter, and 10 meters in height. The feed to a distillation tower is heated by flow through pipes arranged within a large furnace. The heating unit is known as a pipe still heater or pipe still furnace, and the heating unit and the fractional distillation tower make up the essential parts of a distillation unit or pipe still. The pipe still furnace heats the feed to a predetermined temperature, usually a temperature at which a predetermined portion of the feed will change in vapor. By so doing, the lighter, more volatile, products separate out higher up the column, whereas the heavier, less volatile, products settle out towards the bottom of the distillation column. In this slide, you will focus on continuous fractional distillation, the main process of separating the hydrocarbon components of crude oil. Continuous distillation involves feed being sent to the still all the time, and the products being drawn out at the same time. The idea is that the amount going into the still, and the amount leaving the still should be equal to each other at any point in time, at steady state operation. This is different than batch distillation, where the tower has to be intermittently emptied before a new charge of crude oil can be introduced, a process that is not really ideal for the large amounts of crude to be processed. For the fractional distillation, the many types of hydrocarbons present in the crude are separated into fractions of more closely related properties. For example, certain ranges of length of hydrocarbons can be conveniently extracted as diesel, or as paraffin, or as petrol and the like. Crude oil fractions separated by distillation are also changed by subsequent processing into numerous products, ranging from gasoline to diesel fuel, heating oil to asphalt. But given the pattern of the modern demand, which tends to be highest for transportation fuels such as petrol, the market value of crude oil generally rises with increasing yields of light products. The fractional distillation of crude oil is effected under temperatures that can range from 600 degrees centigrade, at the bottom section of the distillation column, with temperatures decreasing to 20 to 25 degrees, at the very top of the distillation column. And through distillation, the mixture can be split into simpler fractions. Small molecules, of low boiling points, are very volatile, and flow easily, ignite easily, and evaporate easily, are collected from the top parts of the column, whilst larger heavy molecules, of higher boiling points, are not very volatile, do not flow easily, do not ignite easily, and do not evaporate easily, are collected from the lower sections of the distillation column. The fractions recovered, starting at the lower parts of the distillation column, comprise of heavy fuel oils and butamen. At a higher level than that, diesel oil, fuel for cars, lorries, and buses, and other heavy industry, generators, are collected. At the further level going to the top, kerosene as a fuel for aircraft is collected, followed by naphtha, which is used to make a variety of chemicals ranging from polymers, other organic solvents, plastics, rubbers, esters, aldehydes, ketones, and other chemicals that can be formed from there. Gasoline, predominantly petrol, used for fuel for cars is collected next, and then, right at the top section, refinery gases are extracted and bottled, and used as domestic fuels, and also as fuels for other industry uses. With regards to the structure length of the carbon chains, starting with the lighter gases that are collected at the top part of the distillation column, petroleum gases will comprise of 1 to 4 on average carbon atoms per molecule. Secondly, gasoline or petrol will comprise of 4 to 12 carbon atoms in the hydrocarbon chain. This is followed, at a lower level than that, by kerosene, which will have 11 to 15 carbon atoms per molecule. Diesel will comprise of 15 to 19 carbon atoms per molecule, whilst bitumen, which is collected right at the bottom, will have 50 carbon atoms plus. Lubricating oil has 20 to 30 carbon atoms per molecule, and is collected at a section higher than bitumen. So, in this regard, we can see how the distillation column is divided into sections, from which the various fractions can be extracted on the basis of their molecular weight. In this slide, you will focus on the equipment that you can choose for the fractional distillation, the main process of separating the hydrocarbon components of crude oil. Firstly, you can choose a packed distillation column, which is filled or packed with material that allows rising vapors to contact descending condensate. The more the vapor-liquid contact, the better the separation. The material you pick for construction should be compatible with the crude oil being distilled. The first type of packing materials that is available to you is helipack, which is formed from a metal wire wound around a twisted rectangular rod. It has a free space of 83%. It is most commonly available in stainless steel but is also available in nichrome, monel, nickel, hastelloeb, bronze, and tantalum. Ceramic saddles. This is an inert packing made of ceramic. It is ideal for corrosive crude oils or those that will react with metal packing. It is not as efficient as other packing types. Rashik rings. This packing is perfect for cases where the crude might be corrosive to, or reactive with, stainless steel. Balls, manufactured from Teflon, or glass. This packing is ideal for cases where packing must be made of glass or Teflon. Wire mesh. This packing is great if you are looking for something that is rugged and industrial. It is normally made of stainless steel. You should use packings as passive devices that are designed to increase the interfacial area for vapor-liquid contact, without causing excessive pressure drop across a packed column. This is important, because a high pressure drop would mean that more energy is required to drive the vapor up the distillation column. Examples of pressure drops you can refer to are given in the table, in this case for a packing called ProPack. You can calculate the number of effective, or theoretical, plates, by dividing the column height by the HETP in the table. The higher the number of plates, the higher the separation efficiency. Secondly, you can also choose a tray distillation column for the crude oil fractionation that you have to do. Each tray essentially acts as a mini column, therefore accomplishing a fraction of the separation task. From this, you can deduce that, the more trays you have, the better the degree of separation. This also applies to the packed column, but here you consider the theoretical number of plates. Overall, for a tray column, the separation efficiency will depend significantly on the way you design the tray. You should design the tray to maximize solid-liquid contact, by paying attention to the liquid distribution, and the vapor distribution on the tray. One type of tray you could consider using is sieve trays, and these are simply metal plates with holes in them. Vapor passes straight upward through the liquid on the plate. The arrangement, number, and size of the holes are design parameters that you can manipulate. You could also consider valve trays. Here perforations are covered by liftable caps. Vapor flow lifts a given cap, thus self-creating a flow area for the passage of vapor. The lifting cap directs the vapor to flow horizontally into the liquid, thus providing better mixing than is possible in sieve trays. A bubble cap tray has a riser or chimney fitted over each hole, and a cap that covers the riser. The cap is mounted so that there is a space between riser and cap to allow the passage of vapor. Vapor rises through the chimney and is directed downward by the cap, discharging through slots in the cap, and finally bubbling through the liquid on the tray. In a crude oil processing facility, after fractionation into different fractions, the separated hydrocarbons can be chemically converted into more desirable reaction products. Such products can be monomers, and unsaturated hydrocarbons that can be used to synthesize a variety of products, such as rubbers, plastic, synthetic fibers, and the like. In this slide, you will focus on reforming. Reforming is a process where you use heat, pressure, and a catalyst, usually containing platinum, to bring about chemical reactions. These reactions upgrade naphthas into high-octane petrol and petrochemical feedstock. An example of a typical form of reforming reaction is the conversion of straight-chain hydrocarbons into cyclic hydrocarbons, such as cyclohexane, and hydrogen. The cyclohexane can be further reformed into benzene, of course, with hydrogen also being formed. Another type of reforming reaction is the formation of branched hydrocarbons from straight-chain hydrocarbons. You can use these branched hydrocarbons to increase the octane value of fuels, in other words, to increase the energy set free on combustion of the fuel. In natural gas-based chemicals production, through the gas-to-liquids technology, also known as the GTL technology, for example at Sasol, reforming is used to produce synthesis gas, for the gas-water shift reaction. You produce synthesis gas, which is composed of carbon monoxide and hydrogen, by reforming methane. The synthesis gas is then used as feed to the Fischer-Tropsch reactor, where a variety of low-octane hydrocarbons, unsaturated hydrocarbons, and oxygen-based hydrocarbon compounds are produced for further separation by distillation. Unsaturated hydrocarbons are hydrocarbons that have double or triple covalent bonds between adjacent carbon atoms. As stated before, in a crude oil processing facility, after fractionation into different fractions, the separated hydrocarbons can be chemically converted into more desirable reaction products. Such products can be monomers, and unsaturated hydrocarbons that can be used to synthesize a variety of products, such as rubbers, plastic, synthetic fibers, and the like. In this slide, you will focus on cracking. You can use cracking to break down the heavier, higher boiling, gas oil from the fractionating tower, into lighter products such as petrol and diesel. You can use thermal cracking, catalytic cracking, and hydrocracking. The first two are included in the diagram. High temperature is used to drive thermal cracking. With catalytic cracking, the cracking at a lower temperature is facilitated by a catalyst. In the diagram, which is for catalytic cracking. The catalyst is regenerated on the left-hand side of the diagram, while on the right-hand side, the various cracking products are separated in a fractionator. In the example of a cracking reaction, it could be hexadecane that is cracked to octane and octene, the latter being an unsaturated hydrocarbon. I would imagine that such a reaction can be accomplished either at high temperature, or in the presence of a catalyst. Octene can be used in the production of polyethylene, the most common plastic. Octane is an 8-carbon alkene suitable for motor vehicles. If you want to increase the octane value of aviation fuel, you can react gases like isobutane and isobutene, using the alkylation process at between 273 and 303 Kelvin. Remember to supply cooling as the reaction is exothermic. It is not indicated on the diagram, but if you want to increase the octane value of motor fuels, you can isomerize N-butane to isobutane, which has a higher octane value. Both have the formula C4H8. Another way to increase the octane value of motor fuel is introducing higher octane polymers, by polymerizing isobutylene and propene under high pressure and temperature, over an acidic catalyst. It also is not indicated on the diagram, but if you need to remove sulfur from crude oil, you can consider hydrotreating, which is mixing it with hydrogen, heating up to 300 to 380 degrees centigrade, and then feeding to a hydrotreating reactor loaded with a catalyst.